Hello, everyone. My name is Anna Veronica Dorogush, and today I'm going to talk to you about gradient boosting and how gradient boosting can be used if you have graph data. First, I'll give you some overview of what is gradient boosting and what are the cases when gradient boosting can be used, and then I will give you some graph data examples. I will be talking about CatBoost library, since this is a library that I have created. It's an open source library. There are also several others. I will be also talking about them. So first, let's talk about what problem we are solving with gradient boosting. Gradient boosting solves supervised learning problem. What is this? In many applications, you have historical data where you have some samples, and for those samples, you know the answers. And what you're trying to do, you're trying to predict the answers for future samples that you have not seen before. This is used in many areas. It's used in medicine, where you have the image, you want to predict if there is cancer on this image or not, or in finance, you want to predict if a person will pay the credit or not, and in many, many other areas. So this is the problem, and there is a bunch of tools to solve this problem, a bunch of machine learning algorithms. Here's the simplest schema that I can give you to solve a machine learning problem. And it's the following. If you have unstructured data, which is music, video, sound, or text, or DNA, and then the best thing that you can do is you train a deep neural network. And in case if you have tabular data is data where every sample is described by a set of features that are not necessarily connected with each other. For example, if you are doing music recommendations, can be then those features can be the length of the track, the name of the track, name of the artist, and so on. In case if you have tabular data, then the best thing you can do is you can run gradient boosting on decision trees. Let's take a look on what is gradient boosting on decision trees. Gradient boosting is an algorithm that builds a lot of decision trees. A decision tree is a structure. It's usually a binary tree where every node is either a leaf or it's a question. Is it an animal? Yes or no? If yes, does it have whiskers? Yes or no? If yes, does it purr? Yes or no? And then we go to the leaf, and the leaf has either an answer, yes, if yes, then this is a cat, or a leaf can have some number in there. That is a decision tree. Now, gradient boosting works in a following way. It's an algorithm that builds an ensemble of decision trees. First, it builds one decision tree so that your predictions have a big error. Then it builds another decision tree so that your error is better. And then it does so for hundreds or thousands of times. And your model can already do very good predictions. That's the algorithm. What are the advantages of gradient boosting on decision trees, and why you should use this? First of all, gradient boosting on decision trees gives state-of-the-art results in terms of quality on tabular data. In most cases, if you run gradient boosting, if you tune it, or even if you don't tune it, you get some quality. This is a very, very good quality. And you can try to do the same things with neural networks. And the best you can do is get to this quality in most cases, or you will just not get this quality. So the best thing for tabular data currently is gradient boosting. The next thing that you need to know about gradient boosting is that it's super easy to use. In many cases, you don't need any parameter tuning. What you do is you just run the algorithm and you get the model. Sometimes you need to tune parameters, but there is a small list of parameters that have to be tuned, and it's not hard to tune them. As opposed to neural networks, where you really have to be an expert to get a good model. And the third thing is that gradient boosting works well even if you have small amounts of data. And also it scales for big data problems. That is a short overview of gradient boosting. There are three main gradient boosting libraries that are in open source and that are available to everyone. Those are XGBoost, that is the first gradient boosting library to be open sourced. It's super popular in the world. The next one is LightGBM. It was open sourced later, and the main thing about this library was its speed on CPUs. So you could train models much faster than XGBoost. And the third one to be open sourced was CatBoost, and that's the library that I have been working on for many years. And CatBoost, the first thing in CatBoost that was different from others was the ability to process categorical features, which I will talk to you, which I will explain in details a little bit later. But what you need to know, there are three gradient boosting libraries. All of them are great. You should use all of them. Let's take a look on CatBoost. So CatBoost is an open source gradient boosting library. It's available on GitHub. It's also available on PyP. You can pip install it. It has 6.3 thousands of stars. If you will use the library, give us a star, give us some love. We will appreciate this. CatBoost is the 7th most popular machine learning framework according to Kaggle 2021 review, along with a list of other ones. I encourage you to take a look on all of them. So what are the applications? In some examples of CatBoost applications are hotel ranking, fraud detection, protection against bots in Cloudflare, in Careem taxi, which is the most popular taxi, for example, in United Arab Emirates, and in a list of other places. CatBoost is used for destination prediction. It's used in JetBrains for code completion, and in many, many other places. It's obviously used for machine learning competitions, especially on tabular data on Kaggle, and used in research a lot. Now, let's talk a little bit about the data that you are running gradient boosting on. As I told, you are running gradient boosting on tabular data. Everyone knows very well that you can, that tabular data can be numerical data. So if you have some numerical features, then you have this table of numbers that you can give to gradient boosting, and you will get a trained model. But that's not the only type of data that can be fed to these models. Another type of data that can be used in gradient boosting is categorical data. CatBoost was the first library to support categorical data, but it's now supported in all three of them. Just recently, XGBoost also introduced categorical feature support. So categorical features are features. A categorical feature is a feature that has a discrete set of values. For example, occupation is a categorical feature because it has values like engineer, designer, writer, and so on. But also some features like user ID or manager ID, they also are categorical. They might be hashes or numbers, but it doesn't make sense to compare them by greater or less, so they should be used as categorical. Categorical features are supported out of the box in gradient boosting. There are also text features. If you just have text, then the best thing you can do is you run a neural network. But if you have a task where you have tabular data, basically, where you have a list of different features, like for if you want to classify something about the film reviews, and you have a list of features about the site, a list of features like a number of likes, features about the user who has written the review, things like that, and only one of the features is text. In this case, it makes sense to use gradient boosting on top of that, and to use this to process this text feature as one of the gradient boosting features. Text features are supported out of the box for classification in CatBoost. So I encourage you to try using text features also. So training gradient boosting is super easy. You can do it in CLI or in R, or you can do it in Python. If you do it in Python, you can use Jupyter Notebook, and basically training of gradient boosting looks like that. You create a model as an object, a model object, and then you call a feed function where you give your training table of your training data. Then you have the trained model. You can look on some visualizations of different losses. You can see how much time has already passed since the start of the training, how much time it has left. But basically, it's very, very simple and obvious how to do this. Now, a couple of interesting things that not everyone knows about gradient boosting. The first one is about training on different hardware. Most of the people train gradient boosting models on CPUs because they, in many cases, they don't know that gradient boosting can be efficiently trained on GPUs. Here you see a graph where on the x-axis is a number of samples. So on the left side, there is a smaller data set. On the right side, there is a bigger data set. And the y-axis shows you the speed up with a GPU usage. There are different GPUs here. The latest one is Voltus. With A100, the picture would be very similar to V100. So you can see that with smaller data sets, the speed up that you get from GPU is about 10x. But if you have bigger data sets, then the speed up will be up to 30 or 40 times. So it's training from GPUs can be very efficient. And CatBoost in particular is tuned to perform well with GPUs. Now, several things about CatBoost versus other libraries. All the libraries are great, and I encourage you to use all of them. But here I will list some things that are nice about CatBoost and different from other libraries. So the first thing is that CatBoost is tuned to perform well out of the box with default parameters without any parameter tuning. So if you just run the algorithm, just run feed function, then you will get very good quality out of the box without parameter tuning. The next thing is that it has sophisticated categorical and text feature support, which is, in terms of quality, it's better. In most cases, it will be better than other libraries. So if you have those types of feature, you should try the library. And the next thing is that the library has very nice model analysis tools and visualizations. So you can analyze what are the most important features in your data set, what are the most important features for a particular sample, how do those features influence this sample, what are the most influential samples in the data sets, things like that. You can look on the graph of, on the error graphs on, for different losses also out of the box. So this is a nice thing. Now, sorry, again. Okay. Now you know a little bit about gradient boosting. You know how it can be used for tabular data, for what types of data it can be used. And one more, okay, from the start of the slide. So now you know a little bit about gradient boosting, you know how it can be used, on what types of data it can be used. But you only know that it can be used for tabular data. In many cases, instead of just tabular data, you have some additional knowledge about pairs of samples in your data set. This additional knowledge can be of different types, and for different types of this knowledge, you can do different things to use those knowledges this knowledge efficiently. The first thing is sometimes in your data set, you know that for some particular pairs of samples, you know that one sample is better than another sample. There should be some notion of what does it mean to be better, but this is a thing that is normally used in ranking. So in ranking, sometimes you do not know like a specific value of relevance, but you can compare pairs of data. You know that one sample is more relevant than another sample. There is a gradient boosting solution in this case. Then other case is sometimes distances between objects. For example, you have your feature space, and one of the features or a set of the features are embeddings of some sort, and they form a space in which you can calculate distances. So if you can calculate distances between objects, you can use this information in gradient boosting. That's the second type of relation. And one more type of relation is just the graph structure. Sometimes you know that different samples, some samples have a relation between each other, and in other do not have a relation between each other. For example, if we are looking on the web pages, then some pages have a link between each other and others do not. Now I will explain you with some examples how this graph information can be used in gradient boosting. Let's first talk about ranking. There is a problem of hotel ranking. What you want to show the user the hotels that he or she will click on. For example, the notion of the click can be different, but let's say it's just a click. So you want to show the hotels that will have a click higher than the hotels that will not have a click. To solve this problem, you can formulate a classification problem. So you can try to predict the probability of the click. And for that, you do not use any relations between samples in your data. But actually, to predict exact value of the probability is a hard problem. It's much harder than just predict the order, than just predict which hotels are more relevant for this user than others. So what people do when they are doing hotel ranking, and in many other ranking systems, they collect the information about pairs of samples or pairs of hotels. They see like one page that they have shown to the user, and they look on pairs of hotels where one hotel had a click and another hotel had no click. And in this pair, they know that one hotel that was clicked is more relevant than another. This way, they can build a data set where they have features about the hotel, or all the features about the hotel, the user, the query. They have all those features. And instead of having the answer column, which will be click or no click, they have the column with pairs, with pair relations where one hotel is better than another. Gradient boosting, all the gradient boosting libraries provide a specific mode for this case. It's called pairwise mode. Basically, what you do, you give to the gradient boosting your data set where every sample is described with features, and instead of a label column, you give a column with pairs. And what the algorithm does, it tries to maximize the probability to rank all the pairs correctly. So that is the situation where you have relations between labels, or kind of relation between labels and objects. There are other relations, there are other situations where you have relation between samples. It doesn't have to be a relation between labels. It also can be something else. So let's go to the distance example. The next problem we will be discussing is called spam detection. In this case, you have a list of features. Let's say you have like domain of the sender, number of recipients, number of links in the email. And you also have a text feature, which is text of the email. And what you have done, you have converted it to an embedding. for example. And in this embedding space, you have distances. So now you are able to calculate distances between samples in your data set. In this case, what can be done, and it really helps, you can add to your features, you can add new features that are based on k-nearest neighbors. Examples of those features are what was the answer for the most similar email in the past. So what you are doing, you are looking at your sample, and you are looking on all the samples before this one in the data set. You are finding the one most similar in terms of distance that you have, and your new feature value is the label in this email. Another example is what is the average answer for top n most similar emails in the past. So what you are doing, you are looking at your sample, looking at all the samples that you have seen in the past. You're looking top k nearest neighbors, and you just average the label. The label here is either 0 or 1 because we are solving classification problem. 0 is if it's not spam, 1 is if it is spam. So the new feature value is the average value of the labels in a top and most similar in terms of this distance samples. One more example would be what is the average answer in a distance-based text cluster in the past. So you can do clustering on your data set, and for every cluster you can calculate the center of the you can and for every cluster you can calculate the average label value for this cluster. Important thing to know when you are doing this trick is the following. If you use the whole data set, then you will have target leakage and it will not work. You will have overfitting. To avoid this problem, what you have to do, instead of looking for like what is the answer for the most similar email in the whole data set, what you have to do is you have to not look on your sample or on any of the samples after this sample, and instead to look only on the samples before this one in time. So to do this, you need to understand what is time, and you can use time for that. That's one option, but that's not the only option. If you do not have any notion of time in your data set, you can just use any random permutation, and that means this way you have some order in your data set, and then you can calculate those features. This trick is called online feature calculation, and yeah, it's used a lot, and in this case it has to be used also. Now we discussed those the features that are using label values and distances. Another option that can be used is to add to your dataset features that are only calculated on graph structure. So in previous example, we were calculating new features that were using label values. They were using only label values of previous objects. So now we will be solving a different task, and we'll be calculating features that are not using label values. Let's say you have a problem where you are doing search ranking. In this case, your samples are web pages, and for every web page you want to calculate a rank. Now web pages have links to each other, and those links form a graph. What you can do is you can add to your dataset new numerical features that are using the graph structure. The simplest thing you can do, you can use PageRank, and that's a very nice feature. So if you have a graph, you just add this, but you can also discover other possible graph properties, like if you have some trusted hubs, you can calculate distance to those in terms of number of edges, or you can calculate relative density of a document cluster or of a sample cluster around this sample. And here, if you are calculating those features, because they are not using label values, you can easily calculate them on the whole data set. So you do not need to use any permutations or any of those tricks. You will not have overfitting if you use those features that are just using the relations between samples and not looking on the labels. Okay, just and not looking on the labels. So those are three main ways to how people are dealing with graph data to use this graph data in gradient boosting, and it's used in many. Sorry, I will repeat again because there was a sound. So those are three main ways how people are usually dealing with graph data when they are willing to train gradient boosting, and it really works well. And because of that, it's used in many production systems around the world. I hope you will try to use those tricks also, and it will be of help to you. Now, I have here on the slide some links to the CatBoost library. Please read about this, try it, and maybe leave some feedback. Thank you so much for listening. It was a pleasure giving this talk. And yes, stay healthy, stay well.